Briefly on pendulums. Pendulums, if you've watched the previous video, you saw my wonderful failure at doing a problem, and that's okay. We're going to get another video here shortly. But for pendulums, things are a lot easier. There's essentially one formula, and we needed to kind of describe this. If you're doing the lab, you've seen the lab. So we're going to draw in a support. That's the support with the cross hatching, and there's going to be, for a ideal pendulum, the mass is all at one point. This has length L, and we can look at the angle here, theta, if we would like. So there's a couple different ways of attacking this. There's a height h in here, and the height h in here is basically L 1 minus cosine theta, right? Because this distance is cosine theta. And so h should be the same length as, this whole thing should be L, and then we're subtracting off L cosine theta. So you can find the energy here. This thing has potential energy is mgh, is mgl, L, 1 minus cosine theta. And then down here, it's going to have kinetic energy is 1/2 mv squared. So you could go through and solve for the energy at any particular, you can solve for the speed at any particular moment in the problem. So you could do that. You could look at the energy, and problems may ask you to look at energy when something's going on like this. All right, so I just wanted you to see that for a moment. But what we're going to do is look at the forces on this thing. And the free body diagram would give us that there is a tension and there is a weight force. But the part that represents the acceleration is that component. All right, there's two components, and you would have T is the weight times cosine theta. We'll draw in theta here again. And then the net force tangent to the circle that it's moving on is going to be mg, the weight times sine theta. And that's going to have to equal the mass times acceleration tangent to the circle. So we can write the acceleration is g sine theta. But we can also write, what is the acceleration? Well, it's a function of its position. Right. So A here is going to be, right, it's the tangential acceleration. The tangential acceleration is r alpha. So it's going to be, A here is L. L is our r now, and alpha is g sine theta. So alpha is g over L sine theta. And in alpha here is the derivative with respect to time. It's two derivatives, second derivative with respect to time of theta. So this is a differential equation. And this is a hard differential equation. This one's not solvable. We have the second derivative of something is a constant times sine theta. It's not strictly easy to solve. However, what we're going to do is make something called the small angle approximation. What we're going to say is, if the angle is small enough, then sine of theta is approximately theta. And this is one of those things you can check. Get your calculator and then put it on radian mode. So for me, it's mode and 5. So it's on radian mode. And then so we're going to say 1 and then sine. And you see it's about 0.84. I'm going to do 0.5 sine, 0.47. 0.1 sine is 0.09. That's close to 1. 0.01 sine is basically 0.01. 0.001 sine is basically 0.001. But it's showing it in scientific notation. But basically, in radian mode, if you put in sine theta, you're going to get theta out. It's going to get closer. It's a better and better approximation. All right, so, and what's happening is theta is getting closer and closer to 0, and so is sine theta. They're getting closer and closer to each other. So that changes our formula. We can sub it in. We'll have d squared theta over dt squared is g over L theta. That has a solution. And the way we solve differential equations as physicists is we go ask the mathematicians. So if you would like to know the explicit way of solving this, you would talk to Mr. Rife, and he'd probably tell you something pretty close to what I'm going to say. We're going to say things that look like this. The solutions is theta is some function, a, times sine of omega t. Right. This is known to be a wave equation in a sense. We're kind of bringing up waves before we do anything else. So this thing kind of has something that looks like this, and omega is the tangential velocity divided by r. So, this has to do with how fast this thing's swaying. But the point of this is we go through this. A here is some function of g and L and some other stuff. But we're going to do a whole lot of dots. We're not going to fill in the blanks here. The punchline here is we can come up with a formula for the period of the pendulum. T here is, well, it's got to depend on L and G because that's what the motion here depended on was L and G. And it'll basically be 2 pi square root L over G. And this is a one equation plug and chug thing. Is if you want to know the period of a pendulum, you measure its length. And then you plug it in and you get T. Now, you could rearrange this. In particular, the useful rearranging for this is to get G by itself. So we square everything and get G up and T down. And so we'll have 4 pi squared L squared over T squared. And this is a useful thing. In the 1800s, this was how you measured gravity. Was you took a pendulum that you knew what time it kept somewhere, and you went somewhere else, and you measured the relative change in gravity by measuring the change in the length of the change in the time of the pendulum. Right, so it stayed the same length. You just carried around, and you measure G by measuring the change in the pendulum. You could do that in this building. You could take a pendulum on a cart, measure it in the first floor, go upstairs, measure it in the second floor. Obviously, we're not going to do that here, but you could do that. It's not going to change that much either. This is a one equation, plug and chug. There's not a whole lot you can do, but other than rearrange it or set up ratio problems. All right, so what I want to do is get to the other bit. All right, because this video is not just about pendulums, it's about oscillations. All right, so let's talk about like a spring that is basically, you've compressed it and then you let it go. Well, the problem that I failed at doing before. What I was trying to get to was that in that situation, you should have an oscillation going on eventually. And so what's happening is we'll start with a spring. It's extra compressed by some mass. All right, so what's going to happen in this case is there is a weight force down and a very, very big spring force up. Okay. Now, the net force here is K delta X minus mg, has to be ma. And that's going to be true no matter what, however we state it. But, eventually what's going to happen is this spring gets longer, and the forces are more balanced. And then the spring gets really long, and eventually the spring is trying to pull the mass back. So you'll have mass times g, and then you'll also have k delta x, and it's now in the downwards direction. But the gist of this is we can find the acceleration based on what's going on in this problem, and with some clever rearranging, we can basically state that this is our acceleration term, and it looks like some constant times x. And the solution for this is exactly the solution we mentioned doing this problem with some constant, with a constant term. So what we're going to have is something that looks like a sinusoidal oscillation. That's kind of what you see is this is, so our equation is going to look like x as a function of time is some constant a. We'll write cosine here. It can be sine or cosine because it can vary depending on the state of this thing. And we'll have our initial, k times x minus omega t. And so what this is going to do is give us, for what we've drawn here, the position. So this is x and this is t. The position here is going to be a sinusoidal wave. And so our amplitude is this height, or it's this distance. Right? It's how extreme does the motion go. And so this thing has a period, big T, and it has this omega, which is what we call the angular frequency. And so the frequency f is 1 over the period. But omega here is 2 pi f. And so it's 2 pi over t. So this thing looks like the angular velocity in rotation, and because it kind of is. We're looking at essentially something that's moving, and because it has this cosine component, we're just looking at motion like this. But something rotating does that motion in the x direction. Now, you can think of A here kind of like a radius in that analogy. This is what we call the amplitude. So now A here is independent of any of these other things about the wave, about the sinusoidal wave, or about the period of, the frequency of this oscillation. A here is based on the energy in the spring. It's based on how much it's compressed, basically on delta x. So we can find the velocity, and as taking the derivative, and that is when we take the derivative of this, and we'll get a omega minus, because derivative of cosine is minus sine, kx minus omega t. And then we'll take the acceleration as a function of time, which is dv dt, or d squared x dt squared. And this is going to be minus a omega squared. There's a minus sign here. I screwed that up. Cosine kx minus omega t, which is minus omega squared. Actually, there's a factor of m here. So this is exactly what it should look like. And what we'll get is omega squared times x of t. And that matches our statement up here, saying the second derivative is the acceleration, is some constant times our original thing. So we have omega squared is k over m. So things like this, if we're talking about the oscillation of an object, we basically go into, we find k, we find the frequency, so we can find omega, and then we can construct these equations. All right, that's what I wanted to do for oscillations. This is preliminary videos. What we're going to do is I'm going to let y'all work on this a bit and have questions, and we'll do some additional stuff later as we need to. We're getting close to the end of the 9 weeks, so I just want to kind of, we'll do this and then we'll do next week's work and see what's up. Yeah, and then eventually you're going to get this final assessment, and I'll get that eventually. But the last two things I wanted to do is springs and pendulums and oscillations and fluid, and it's a whole lot of working with forces and energy. Again, it's applied stuff. So we're going to, let you stew on that for a little bit, and then when you have questions, we'll come up with the appropriate stuff. We've got basically 1 week's worth of work left and 2 weeks in which to do it. I've kind of scheduled, give you that last week to work on the assessment and to finalize your work. So we've got a little bit of flexibility here, but we're running out. You got 14 calendar days till the assessments. So you got to get working here. All right. Let me know if you have any questions.